Okay, so this video is part 3 of this problem, and let me just quickly explain the setup of the problem so that we can place the premise and the requirements of this problem clearly before we start solving it. Over here we show a curved surface whose curvature changes along the trajectory of the surface. There is a disk of radius r that rolls without slipping, and as it rolls without slipping, the point of contact on the ground, which is given by O prime here, this is the point of contact on the ground, moves with a constant velocity v0 tangential to the surface. We are given a point, an arbitrary point P, on the periphery of this disk, and which is making an angle theta with respect to this line, and this line is basically the line joining the instantaneous center of curvature of this curved surface and the center of the disk, C and Q. So C and Q forms a line which passes through the point of contact, and so it is C O prime Q, and angle theta is being measured from that line in the clockwise direction as the disk rolls. This is another orientation or another configuration after the disk has rolled along this curved surface. Here, as we can see, because of the spinning of the disk, the point P has turned further away from this line. This line is still the C O prime Q, the line joining the instantaneous center of curvature of the path and the center of the disk, passing through the point of contact O prime. As you can see here, the radius of curvature is different than what was over here. Still, the point O prime has that same constant velocity v0. We are asked to use the unit vectors ET, EN and EB, a normal tangential coordinate triad, to solve this problem. The problem asks for the velocity of the point P at this arbitrary configuration. Both of these two are arbitrary. This is just a few instances or sometime after this instant, we are to find the velocity of the point P and the acceleration of the point P. Now this is a problem where if you are thinking of direct differentiation of the position vector of P to find its velocity and acceleration, then that approach may not work. And that is so because in order to express the position vector of the point P in the most general form, you need to have a fixed reference point. Now in this problem there is no fixed reference point. Okay, the radius of curvature changes along the curve, so there is this curve on which the disk is turning and moving does not have any specific center. So it is, and so you have to arbitrarily choose some point, and so that will lead to additional introduction of variables. And so while it may be possible to do it, it may become overly cumbersome to carry out direct differentiation of position to find the velocity and then the acceleration. So that method is not very efficient in this particular problem. In the prior two videos on this problem, what we did is that we first found the velocity of the point P using a rotating reference frame, and then after we found the velocity of the point P, we took two approaches to find the acceleration. One is we took the velocity and directly differentiated it, to find the acceleration. So that was one approach to find the acceleration. The other approach was to again use the rotating reference frame, and write the overall relative acceleration expression in rotating frame, which consists of 5 terms, and then fill in those or populate those different terms by calculating the individual vectors and doing their vector operations. So we have given 2 methods for finding acceleration. For finding velocity, we have given one method where we have used a rotating frame, and as I mentioned, direct differentiation of position is not an efficient method for this problem and may not be even possible. Now in this video, what we'll do is we are going to change the rotating frame of reference and resolve the velocity and acceleration. This exercise is especially important for students that are learning motions in rotating frames, because it can be confusing as to how to perceive these motions in different rotating frames. What is the difference between rotating frame and triad? So one of the goals of these videos is to actually explain this. And in my view, a good way to explain this is to take a problem and then solve it using multiple rotating frames. And hopefully, as the student who is trying to learn compares these methods, velocity acceleration calculation in one rotating frame versus in another rotating frame, if these two are directly compared, then hopefully the student learning these concepts will be able to see more clearly as to what these vectors represent, how to physically interpret these vectors, and then formulate them. So with that goal, we will start solving this problem with a different reference frame. So let me just go over the things we have articulated here. So determine the velocity and acceleration of P. That is, of course, what we want to do. We still want to use the same triad ET, E, and EB. So keep in mind the triad is different from the rotating frame. You can have 2 different rotating frames of reference to solve a problem, but both of them using the same triad. That is the case here. This is a reference. For reference, this is the velocity expression. I didn't write the acceleration expression because it was too long, but we are going to derive it. And the reason for writing this is that once we derive the velocity expression using now a different reference frame, then we'll compare it against this to make sure that it is right. We will also verify that we obtained the same acceleration by comparing the acceleration results in the previous videos. For the purposes of this calculation, we are going to just use theta dot equals these results. Theta dot equals V naught over small r was a result that was derived in the prior video, or maybe in the first video. So please go over that, and I'm just going to use this result in the interest of time. Furthermore, in the previous 2 videos, we have also used extensively the time derivatives of the unit vectors ET dot, EN dot, and EB dot. We have derived these and used them. So we are not going to rederive them, but use these results. Okay, so now let us get to the rotating frame that we are going to use. In our prior rotating frame method, we used the rotating frame of reference to be that which is fixed to the disk. So that means the rotating frame was a body fixed frame that was turning with the disk. And so that frame of reference, its rotational speed was the absolute rotational speed of the disk. In this part, what we'll do is we'll change that rotating reference to now be attached to CQ. So this line CQ is going to be the rotating frame for us. As it turns, our rotating frame turns with it. Okay, so previously our rotating frame was attached to the disk. Now our rotating frame is attached to the line CQ. Okay. So now when we attach the rotating frame to the line CQ, it will be easier for us to express the velocity equation, velocity of p with respect to O prime, because when we choose this new reference, the rotating reference to be fixed to CQ, when we write the equation Vp, we can write it as Vp equals Vq plus omega cross rho p with respect to q plus rho dot p with respect to qr. We can do that, or we could write it as Vp equals Vo prime plus omega cross rho p with respect to O prime plus rho dot p with respect to O prime r. So we could actually take either of these approaches. The only thing that we have to be careful about when we do this is that now we are choosing our rotating frame to be attached to CQ. So therefore omega is going to be the angular velocity of CQ, and the angular velocity of CQ is V naught over capital R EB. Okay, so that is something that we need to incorporate. Furthermore, if we use the first equation, then VQ would be and we have derived this before. I'm just going to repeat that here. The result here, VQ is going to be V naught divided by R times capital R plus small r ET. Okay, so if we use the first equation, we would be using VQ. If we use the second equation, we would use Vo prime, right? And Vo prime is that constant velocity V naught ET. Okay, if we used the first equation, then rho p with respect to q, we have derived it before. It is r sine theta et minus r cosine theta en. Okay, that is if I use the first equation. If I use the second equation, rho p with respect to O prime is going to be equal to, if we go back to this figure, p with respect to O prime is essentially this vector, and this vector is r sine theta in the ET direction and minus r plus r cosine theta in the EN direction. So r sine theta in the ET direction and minus 1 plus cosine theta r in the EN direction. Right? Now another important thing is, when we use this CQ as our rotating frame, then we are essentially considering our rotating frame is not fixed to the disk anymore. Okay, it is fixed to CQ. So even if we use P and if we express the first equation with Q as the reference variable, we have to treat Q and P to be two independent points and not fixed to the same rigid body. Keep in mind, and so if you go back to the prior video, you will see that in the prior video we were able to just say, or we were able to cancel this term, and we did that on the basis that P and Q are on the same rigid body, and so remember this, and and our rotating frame of reference was fixed to that rigid body. Now if we use CQ as our rotating reference frame, although P and Q are on the same rigid body, but since the rotating frame is not fixed to the rigid body, then this term will still be there. So we will have to differentiate this, okay, under the condition that ET and EN are not changing, to find the derivative inside the rotating frame. So we will have to do that. And of course, if we use O prime as our reference point, then we have to do that because anyway our O prime and P are not on the rigid body. That is, and of course we are using CQ, which is not fixed to the rigid body. So in this case, we anyway have to do, even if we used Q, just because our rotating reference frame is CQ and not attached to the rigid body, we would still have to differentiate this term if we took this approach, this reference frame, okay, because in this reference frame, P is moving with respect to Q in this reference frame. It is if the reference frame was fixed to the rigid body, then P would not be moving with respect to Q in the rotating frame, and hence we wouldn't have to have that differentiation. So there is a subtlety which I would urge you to think about. Okay, so let's go ahead with our velocity calculations. So we will go with Vp is equal to Vo prime plus omega cross rho P with respect to O prime plus rho dot P with respect to O prime in the rotating frame. This is the equation. We have written all the expressions, so we are going to plug in. Vo prime is equal to V naught Et plus omega is V naught over capital REB plus the rho P with respect to O prime. Is going to be, we have written in the last page, I'm just going to rewrite it here, R sine theta Et minus R1 plus cosine theta En. You just check, yes, plus this term, this derivative, rho dot P with respect to O prime R. So let's calculate this. This is the rate of change of P with respect to O prime in the rotating frame. To find it out, what we do is we are going to carry out the derivative of rho P with respect to O prime. But we are going to keep our unit vectors constant, which means that we are doing the differentiation inside those unit vectors, so inside that rotating frame, okay. So it would be R cosine theta dot Et minus R1 plus this should be plus R sine theta dot En. And note that I am not going to put the En dot and Et dot because I am taking the derivative inside the rotating frame, okay. I'm trying to find out how this vector is changing inside the rotating frame. And if you think about it, inside this rotating frame, the only motion that this disk, the disk has is the spinning motion. So inside this rotating frame, the only variable that is changing is theta. So theta dot is the only thing that is changing In other words, if you fix yourself to this rotating frame and you are moving with CQ, okay, then the rotation that you will see is what you will see the disk to be doing is just spinning. So you will see that the disk is spinning about this axis, and so that needs to be just incorporated, and so therefore only theta dot will then show up. I'm not going to differentiate ET and EN because ET and EN are already fixed to this rotating frame, okay, and so when I consider motion inside the rotating frame, for that purpose ET and EN are fixed. So substituting for theta dot, I have so theta dot was V0 over small r, so I have V0 cosine theta ET plus V0 sine theta EN. So that's the expression of the of rho dot r. So therefore the velocity of the point P is equal to V0 ET plus this one should be a cross product. I'm sorry, this is omega cross rho P with respect to O prime. So this is not a plus, this is a cross product. Now I need to carry out this cross product. EB cross ET is let me just see here. EB cross ET, our coordinate frame is ET is like this, EN is like that, and EB goes into the page. So EB cross ET is EN. So we have V0 over capital R times small r sine theta EN, and EB cross EN is negative ET. So we are going to have plus V0 over capital R times small r to 1 plus cosine theta ET, and then we add to these two terms V0 cosine theta ET plus V0 sine theta EN. So now combining the terms, so all the terms containing ET, so let's put them together. We'll have V0 1 plus cosine theta plus V0 small r over capital R 1 plus cosine theta ET. So that's in the t direction, plus V0 sine theta times 1 plus small r over capital R EN. So simplifying one more step here, we would have V0 1 plus cosine theta times 1 plus small r over capital R ET plus V0 sine theta times 1 plus small r over capital R EN. That's our expression for VP, and if we compare it to the expression obtained for VP in our previous method, we see that we have exactly gotten the same answer. V0 sine theta 1 plus small r over capital R in the EN, that's what we have here, and V0 1 plus small r over capital R times 1 plus cosine theta, that's what we have in the ET direction. That's exactly what we have here. So that is the velocity calculation. We are not going to do the acceleration calculation in this video, rather we'll stop the video here, and in the next video we are going to do the acceleration calculation with this reference frame. Keep in mind that in this video what we have done for this problem that we have been working on in the prior 2 videos we have changed the reference frame, rotating reference frame. Now our rotating reference frame is CQ, which joins the instantaneous center of curvature of this path to the center of the disk, and with that as our rotating reference frame we are solving for the velocity and acceleration of P, and we have discussed about how to set up the problem, and we went ahead to find out the velocities. One of the distinguishing features with this rotating reference frame is that now we have to use all the 3 terms in the velocity. We could not ignore this third term which has the velocity in the rotating frame, and that is because the points P and Q or P and O prime that we consider, whichever approach we take to solve this problem, will not be considered to be on the same rotating reference frame. Okay, so that's why we have to have that third term. You can go ahead and we have solved the problem with this formulation for P, but you can go ahead and solve this problem with this reference frame for this formulation where P is expressed with respect to Q, and you will find the same velocity. You can verify it. In the next video we'll go through the acceleration calculations. Thank you very much.